enthalpy of atomization. Enthalpy of atomization is delta atomization H. So how do you define delta atomization H? So what happens is, it is the enthalpy change I told you, moment the word enthalpy comes in, what are we talking about? We are talking about 1 mole, remember that. Is the enthalpy change accompanying the dissociation of all molecules in 1 mole of a gaseous substance, into atoms in gaseous phase. So in other words, what are we talking about? Suppose if I have chlorine which has got only one single bond. Now 1 mole of chlorine molecule, that means 6.022 into 10 raised to 23 molecules, breaking that single bond and forming chlorine atom in the gaseous state. Of course, it will form 2 moles of chlorine atoms in the, we are not bothered about this, we are bothered about this. 1 mole of chlorine, what do you call? Molecule. It's a diatomic molecule. So what is going to happen? This delta H, delta atomization H, will be equal to what? It is 240, it is plus 242 kilojoule per mole. But imagine if it is a polyatomic molecule. For example, methane. So in methane, what is going to happen? 1 mole of methane, first 1 bond will be broken. So you will have H and then you will have CH3. Let's say this is X value. Then CH3 is going to break to form H plus CH2. Then what is going to happen? CH2. So let us say this is Y. This is going to form what? H plus CH. Then CH is going to form H plus C. Or in other words, the net reaction is what? CH4, 1 mole, the dissociation of all molecules, complete dissociation of all methane molecules into straight away 4 hydrogen atom and 1 carbon atom in the gaseous state. So this is X plus Y plus Z. So sum total of X plus Y plus Z, it will not be same. First point is, each of this value is not going to be same. Why? I'll explain. Sum total of this value is equal to plus 1660 kilojoule per mole. This is not going to be same. Why? Because here your methane carbon was sp3 hybridized. So you are breaking a sp3s overlap to form this. But moment it became a methyl carbon free radical, carbon has become sp2 hybridized. So now the carbon hydrogen bond in this case will be a sp2s overlap. Then this will be a sps overlap. Then this will be plain sp overlap. So each values are going to be different. but the consolidated value is 1660 kilojoule per mole. So 1660 kilojoule per mole divided by 4, this will be how much? 1660 divided by 4. So each one, so for each bond, it will be 415 kilojoule per mole. So this 415 kilojoule per mole is what we are talking as average bond energy for a CH bond. It's not the actual value, it is the average. You got CH bond in methane, methylene, methane, methyl, methylene, and then CH bond. The total you found out and then divide by 4. So that will be the average energy for one CH bond. One CH, there is no double bond, CH bond. Is this point clear? But this will be the enthalpy of atomization. This will be enthalpy of atomization, and this will be bond energy of, BE means bond energy of a CH bond. Average energy required to break a CH bond in a alkane, average energy will be plus 415. It doesn't look like plus, yeah, now it looks like plus 415 kilojoule per mole. I hope you have understood the difference, because later on I need this concept, finding out the enthalpy using bond energy. Okay, then we have of solution. Okay, so when we talk of enthalpy of solution, that is delta solution H. We'll define it, we'll leave space. What does it depend on? So when you dissolve a substance in water, it is enthalpy of solution. But what does it depend on? It depends on, first of all, the solute-solute interaction. What does it depend on? It depends on the solute-solute interaction. Okay, so this will be lattice energy. Then you have solvent-solvent interaction. And the third one we have is solute-solvent interaction. Solute-solvent, all these three go to making up the enthalpy of solution. So first we will define what is enthalpy of solution. Then from this we will derive the Born-Haber cycle. So enthalpy of solution is defined as, it is the enthalpy change. It is the enthalpy change. It is the enthalpy change when 1 mole of a substance, mainly ionic substance, because all this is concerning, you can't have sugar, you can have NaCl, you can have KCl, calcium chloride, something. 1 mole of a substance, 1 mole of a substance is dissolved in a certain fixed volume, a specified quantity of, solvent. So you have taken 1 mole dissolved in 1 liter, that has to be mentioned. 2 liters, 3 liters, but you have to mention specified quantity of the solvent to form a solution of a particular concentration. So now, what does it involve? Suppose you put, let me explain this. Suppose you put NaCl in water. So you put NaCl, an ionic compound. Now NaCl was a solid when you put it. When you put it in water, what happens? When it was a solid, there was a force of electrostatic force of attraction which was holding the sodium ion and chloride ion. So first when it goes in, step 1, what has it to do? It has to overcome this sodium chloride force of attraction and become sodium ion and chloride ion. So that is what is solute-solute interaction. Then there is going to be slight van der Waals forces which are holding the solvent. They also have to break. So that will be not much, but that will be solvent-solvent interaction. Solvent-solvent interaction. Okay. The third, so this was second one. The third point is, now you have the solute particle Na plus and you have the water molecule. Okay. Then you have Cl minus, you have water molecule surrounding it. They are going to form a bond. They are going to form a bond. So water forming a bond, because water is a polar molecule. If I magnify this, what is going to happen? You have Na plus and you have HOH. So this is delta plus delta negative. So it's going to form a bond. Another HOH is going to form a bond. Another HOH is going to form a bond. Another HOH is going to form a bond. Same way with chloride, what is going to happen? HOH. Then we have HOH. So there is going to be a bond between chloride and H of the water. So this is a solute solvent interaction and it's called as hydration. It is called as hydration. So one very important point is heat of hydration is always exothermic. So this is one question which they always ask. Which enthalpies are always exothermic? Combustion, neutralization and hydration. Combustion, neutralization, hydration. One more is there, we will come across that. So these are always exothermic, whereas others are exothermic or endothermic, but these three are exothermic. We are going to study neutralization, combustion also in thermochemistry in next lecture. So first we talk about is a solute-solute interaction. This is clear. So the energy, now what happens is, in ionic crystal, what is happening? There is an electrostatic force of attraction between the oppositely charged ions. Between the oppositely charged ions. So in water, this force has to be overcome. The energy required is called lattice energy. Delta lattice energy H. So for 1 mole. So how do you define lattice energy? You define lattice energy as the enthalpy change when 1 mole formation, either it is dissociation of 1 mole or formation, because if it is formation, it is exothermic. When you put it in water, it has to, that much energy has to be given to break it, then it will be endothermic. Is this clear? So we decide in terms of formation. So lattice energy is defined as lattice energy. So delta lattice energy H. It is defined as what? It is defined as enthalpy change. It is the enthalpy change accompanying the formation of one mole of formula unit of crystalline solid from what? From its constituents ion in gaseous state. So sodium ion in the gaseous state plus chloride ion in the gaseous state forms NaCl. So this formation is exothermic. So that's exactly the energy that you have to supply in the solution to make it convert it back into sodium ion and chloride. So this is exothermic. So in the solution, when you talk in terms of solution, it will be endothermic, it will be positive. Now there is a lot of scope for asking questions in this. Is this clear? So what is this lattice energy dependent on? Lattice energy is dependent on, so lattice energy is dependent on cationic and anionic radii. Cationic and anionic radii. So let us look at an example. We have, suppose if I take lithium fluoride. So I have taken small atom, smaller cation, smaller anion. Lithium chloride, lithium bromide, lithium iodide. Very important topic. That's why I'm discussing in detail. This will be minus 1037 kilojoule per mole. This is minus 852. This is 815 minus, and this is minus 761. So what can you see over here? You can see that the cationic size is remaining the same, but the anionic size is increasing, so lattice energy is decreasing. So what can we say? Smaller anion will be having a larger lattice energy. Then let us go to the next step. Let's look at the, okay, we have lithium, then we have sodium, potassium. Okay, so we have potassium fluoride and sodium fluoride. So now what happens? Your anion is small, but your cation size is increasing. So what is going to happen over here? This will be sodium fluoride is minus 926. This is minus 821. Let's look at the what you call other PA. When we are talking about potassium largest size, talk about potassium iodide, it is minus 649. I am not writing the in between values because I have to come to the conclusion. So smallest, so what do you realize over here? Maximum value of lattice energy is lithium fluoride and the least value is potassium iodide. Why? So when will the lattice energy be more? If they are giving a comparison, they might just give you all this lithium fluoride, sodium chloride, which will have the maximum lattice energy. So smaller cation and smaller anion, lattice energy increases. That's why lithium fluoride has the maximum lattice energy and potassium iodide, largest cation. So you can have lithium, sodium, potassium, rubidium. So rubidium iodide, cesium iodide would probably have the least, what do you call? Lithium, sodium, potassium, rubidium, cesium. Yes. So rubidium would be the last one, because cesium is a liquid metal. Cesium is what do you call cesium radioactive नहीं है, francium is radioactive. हाँ, so what will be come to, which will have the least will be cesium iodide. Cesium iodide will have, so maximum lattice energy, I am talking about an entrance exam question, smaller cation, smaller anion, maximum lattice energy, it is clear. Whereas larger cation, larger anion, least, so look at the extreme, these two are going to be the extreme, largest and the lowest, is this point clear? Then solute-solute interaction is over. Interaction, those are weak van der Waals forces. They are not going to contribute much to what you call so these are energy required to push the solvent molecules apart. Not very large or of consideration. Then we have solute solvent interaction. That is very important. What did I tell you? That is called as hydration. So enthalpy of hydration. And what did I tell you? Most important point, hydration is always an exothermic process. And then one more thing, you know, why is lithium the strongest reducing agent? It has the highest enthalpy of hydration, remember that, okay. This is how when we are teaching, the questions have to be what you call generated, enthalpy of hydration. So delta hydration H. So what is enthalpy of hydration? It is defined as, I am taking the definition as per some textbook because the language should not differ, okay. So it is defined as the enthalpy change involved in hydration of 1 mole of gaseous ions. 1 mole of gaseous ions. So sodium ion, what is happening? It is getting surrounded by water and forming a bond, and bond formation is exothermic. Is this clear? Now, so if you summarize all this, mathematical expression that we get is enthalpy of solution is the summation of delta lattice energy H plus delta hydration H. Very important. In this you can see that lattice energy is endothermic, hydration is exothermic. So the net of this, now we will answer. See what happens is, why is silver chloride sparingly soluble salt and why is sodium chloride freely soluble salt? See, in this case what happens, whenever we dissolve something, where is the heat going to come? The heat is going to come from the solution. If this heat energy is more, what happens? That will be more than what you call the energy required for it to dissolve, and then it will dissociate. In this case, in the case of silver chloride, the energy which is required is much more than what can be supplied by solution. So very small amount of it dissolves, and whatever dissolves dissociates. So enthalpy of solution dictates whether a salt is sparingly soluble or it is what you call freely soluble. Is this clear? Now let us understand the values. Okay. So if I take example of, let us say, lithium chloride, sodium chloride, potassium chloride. Okay. So I can see that lithium chloride smaller cation, larger anion. So when the cation is smaller, when the cationic sign is smaller, just imagine now lithium ion is small. Okay. So lithium means, lithium was what, if you remember, 1s, the lithium 3, 1s2, 2s1. So here the protons, 3 protons, and this is 2 electrons. Now because it is very small, what is going to happen? The water HOH, it can easily pull the oxygen of the water and hold it strongly. So smaller the cation, it is able to bond much more strongly with water. So heat of hydration will be more, stronger bond, heat of hydration will be more. When heat of hydration is more, what is going to happen? It's going to be exothermic. So in this case, your heat of solution, delta solution H, what is going to dictate? The size of the cation. Look at what you call lithium chloride, it's minus 37 kilojoule per mole. Whereas in case of sodium chloride, it will become positive. 3.9 KCl is 17.2. Now from chloride, if you go to bromide, so lithium bromide. Now what have you done? You have kept the smaller cation but larger anion. Then what is the effect of that? Lithium bromide is minus 48.8 kilojoule. So what can you say? Smaller cation and larger cation and larger anion, the enthalpy of solution increases. So you have to look. So lithium iodide will have the maximum enthalpy of solution. Smaller cation and larger anion. Are you understanding? So this is how we have questions placed. So if you have lithium chloride, lithium bromide, lithium iodide would have had the maximum value of enthalpy of solution. So this is how questions are framed. Okay. So this was about enthalpy of solution. There is one thing called as enthalpy of dilution. Enthalpy of dilution. In some cases, this can be what you call very large value. Delta dilution H. Just imagine if you take sulfuric acid and add it in water, what is going to happen? It's highly exothermic. So when you dilute, what happens? Sometimes it is exothermic, sometimes it is endothermic. Is this clear? So how would you define enthalpy of dilution? The enthalpy change when a solution of one concentration is diluted to form a solution of another concentration. So you have 1 molar sulfuric acid, you make it 0.1 molar, some amount of heat is released, that is enthalpy of dilution. Is this point clear? Not of much significance, isliye I am not taking great into. Now what happens is we studied so much of these enthalpy change during physical change. It is not necessary that you can find out all of them. And one of the most difficult ones to find out is lattice energy. So lattice energy is always what you call found by indirect method. So how do we do that? See, it's very simple. Let us say Born-Haber cycle for sodium chloride. Lattice energy we want to find out. Basically, what is one formation of sodium chloride? 1 mole of sodium in the solid state plus half a mole of chlorine in the gaseous state formed 1 mole of what you call sodium chloride. What is enthalpy of formation? That's the next day. When 1 mole of a substance is formed from the elements, abhi tak gaseous we were talking, formed from the elements in the solid state forms sodium chloride solid. Now this value is enthalpy formation H. I'll again repeat. So what is the enthalpy of, what is the enthalpy of formation of a substance? Enthalpy of formation of a substance is defined as the enthalpy change when 1 mole of a substance is formed from the elements in the standard state. So sodium element is in that, at say room temperature, is solid, chlorine is gas, sodium chloride is solid. Now what happens is, see this sodium solid 1 mole, when you make it sodium in the gaseous state, directly from solid to gas, what is this? This is delta sublimation H. Now this sodium in the gaseous state, you make it to sodium ion in the gaseous state. This is delta ionization enthalpy. Half a mole of sodium to make it to 1 mole of chlorine atom. This is half the delta atomization H. Enthalpy change required for 1 mole of molecules to be converted into gaseous atom, but there is in the reaction half a mole of chlorine molecule is there, na? 6.022 divided by 2, that into 10 raised to 23, that much atoms are there. So the value has to be also divided, because it's not for 1 mole, it is for half a mole. Now this chlorine, you are making it into chloride ion. So this is delta electron gain enthalpy H. Now sodium ion and chloride ion are combining to form sodium chloride solid. This is delta lattice energy H. This much is the energy released when sodium ion in the gaseous state combines with chloride ion in the gaseous state to form 1 mole of sodium chloride. So now what does Born-Haber cycle say? Okay, so your delta H formation, delta formation H will be equal to delta for sodium, it will be delta sublimation H plus delta ionization enthalpy H. Okay, then we have got for chlorine, what do we have? Plus half. So I like this sodium, so it becomes easy. This is for sodium plus half delta atomization H plus what? Delta electron gain enthalpy H plus delta lattice energy H. All this will be there. So this value we know, this value we know, this is for chlorine, all these values we know. So you take all these values over here. Final formation H was minus 411. How much was all this? This was equal to plus 379, this is kilojoule per mole, kilojoule, plus delta lattice energy H. So if I take this over here, I have added all this, I am not giving the values. So minus 411, this plus became minus, minus 379 is delta lattice energy H. So your delta lattice energy H for sodium chloride becomes minus 790 kilojoule per mole. So I need that you should know this value. I said 790, it is 790, so you have to know this, because this is a very common Born-Haber cycle which is taught in all levels, 11th, 12th, anything. So we need not need to know the formation, all these values, we have to know this, that the lattice energy of sodium chloride is minus 790 kilojoule per mole. Have you understood? So this is two things: thermochemistry, thermochemical equations. What are the points we have to know about thermochemical equation? And we'll look at one of them. Then 2, 3 we can always talk next lecture. So what is thermochemistry? Thermochemistry is the study of heat change or heat content change. Okay, study of heat content change is the study of heat content change. So that heat content takes care of the enthalpy word. Study of heat content change during a chemical change. During a chemical change. Then what do we have? We have a thermochemical equation. So what is a thermochemical equation? An equation which summarizes an equation which summarizes the enthalpy change or the heat change or the heat content change is a thermochemical equation. So what is the mathematical expression for thermochemical change or heat content change? Delta H will be summation of enthalpy of product minus summation of enthalpy of reactant. Now you'll ask me, sir, nowhere we have been only discussing enthalpy change. Where did this enthalpy come from? Is this clear? So now what are the conditions that we have to know, and what conditions are we doing this? First of all values are taken in standard state. All values are taken in standard state. See, there's a very big difference between standard temperature, pressure and standard state. Standard temperature pressure is 0 degrees, 1 atmosphere pressure. Standard state means it is 298 Kelvin or 25 degrees centigrade and 1 atmosphere pressure. Because we never do any thermochemical any heat change at 0 degrees. So that is not applicable to thermodynamics. It is clear. Thermodynamics normally we do at room temperature. So we have taken 25 degrees centigrade as the base. First point, all values. Second, while writing the thermochemical equation, while writing the thermochemical equation, the phase of substance in standard state must be mentioned. For example, if I am saying C plus O2 forms CO2, this is an incomplete thermochemical equation. Why? Because at 25 degrees centigrade, what phase it is? It is solid, the physical state. Either you say phase or physical state would be a more correct answer. The physical state of substance should be mentioned. So at 25 degrees centigrade, carbon is solid, oxygen is gas, carbon dioxide is gas. So then this becomes a complete thermochemical equation, because physical states at standard state must be mentioned. The third most important point is enthalpy of element. Very important. Enthalpy of elements in their standard state, in their standard state is taken as zero. Very important. It's not zero, it is assumed to be zero. Is taken as zero or assumed to be zero. Because absolute enthalpy cannot be found out, I just now told you. I told you that absolute enthalpy cannot be found out. Why it cannot be found out? Because then you are talking about the internal energy, which involves rotational motion, translational motion and all that, which are microscopic properties. So somewhere we have to have some benchmark. Na? So we said if in any chemical change, elements are there in their standard state. So carbon gaseous plus oxygen or gas forms CO2. There you can't take carbon as enthalpy to be equal to zero. Why? Because carbon solid has to be converted to carbon gas. Enthalpy of sublimation is there. Na? In the standard state at 25 degrees, what is the state of carbon? It is solid. So its enthalpy is taken as zero. Are you understanding? So whatever elements is there, that is taken as zero. So now we come to the first thermochemical equation, that is, I have to explain in great detail. Enthalpy of formation. So that is called as delta formation H. What is the definition of enthalpy of formation? It is defined as the heat content change or the enthalpy change. It is defined as the heat content change or enthalpy change accompanying the formation of one mole of a substance from its elements in their standard state. So 2H2, I am just giving you an example, 2H2 plus O2 forms 2H2O. So H2 gas, oxygen gas, water will be liquid at STP, at standard temperature, not STP, I'm sorry, at standard temperature, 25 is liquid. So can I say this is enthalpy of formation? No. I cannot say. Why? Because it says 1 mole should be formed and this value is 2 moles. So this value, whatever enthalpy change value, divided by 2 is enthalpy of formation. Why? Because whatever value you got, that was for formation of 2 moles, whereas we have got only 1 mole. Definition says only 1 mole. Now second expression, if I say, suppose CO plus half O2 forms CO2. This delta H is minus 110 kilojoule per mole. Can I say this is heat of formation because 1 mole is formed? No. The second condition, this is carbon monoxide, this is a compound. This is a compound. Our definition says that your reactants have to be elements. Product has to be 1 mole of the products. 2 conditions have to be fulfilled. Your reactants have to be elements in a physical state at 25 degrees centigrade, whatever they are, and the product should be 1 mole of the product should be formed. So now if I say carbon solid plus O2 gas forms carbon dioxide gas, delta H, I think it's about minus 330 kilojoule, around that, let's take it. Then this will be enthalpy of formation. Why? It is fulfilling both the condition. 1 mole of product is formed and the reactants are elements. Physical state is what they are at 25 degrees centigrade. Carbon is a solid, oxygen is a gas. So that is the importance of this definition. So enthalpy, now one more thing, I have to tell you, sometimes students get into this habit of thinking enthalpy of formation is exothermic. No. Enthalpy of formation can be exothermic or endothermic. Enthalpy of formation delta formation H can be exothermic or endothermic. Both are possible. Enthalpy of combustion. Enthalpy of combustion. So delta combustion H. What is the definition of enthalpy of combustion? The enthalpy of the heat content change accompanying the complete combustion of 1 mole of a substance, in excess of air or oxygen. So can I say C plus half O2 forms CO, the delta H value is minus 220 kilojoule. This is heat of combustion? No, because generally formation of carbon monoxide is incomplete combustion. If you were to burn carbon in excess of air or oxygen, it will only form carbon dioxide. So remember, in any reaction, from the entrance exam point of view, in any reaction when there is a formation of carbon monoxide, that equation is not going to be considered as enthalpy of combustion. What will be enthalpy of combustion? Carbon plus oxygen forms carbon dioxide, whatever is the value. Then suppose benzene, C6H6 plus 7.5 moles of oxygen forms 6 CO2 plus 3 H2O. Now we will ask, is this enthalpy of combustion? Yes. Why is it yes? Why? Because benzene 1 mole was there. Now 1 mole required only 7.5 moles. What can we do? That is a coefficient of balancing that we have. So people look at that 7.5 moles and think it is incomplete combustion. No. For complete combustion of 1 mole of benzene, you may give 10 moles of oxygen, but only 7.5 moles are required for complete combustion. It forms 6 CO2 plus 3 H2O. So this will be also considered. So don't get confused by that 7.5 factor. For complete combustion of 1 mole of benzene, only 7.5 moles are required. That's fine. And it will be enthalpy of combustion. Is this clear? There is then enthalpy of